Yes, I don't have enough time.
Okay. Our last speaker of the section is, sorry, give me 1 second, Li Fan Gao.
Yes.
Thank you. So he is a PhD student from the mechanical engineering department from the University of
The
New
Stony
York.
Brook University. Yeah.
Cool. And he is going to talk about, I'll let him introduce.
Okay. Good afternoon, everyone. My name is Yingheng Gao, and I'm a PhD student in the Department of Mechanical Engineering at Stony Brook University. And the topic of my today's presentation is multi-material topology optimization of the circuit Halbach array by using the Cardinal basic function-based level-set method. And this work is sponsored by the U.S. Department of Energy and the National Science Foundation, and also GE Vernova. Okay, so I'll start with the introduction and background. So first of all, so what is Halbach array? So Halbach array is a special arrangement of the permanent magnet, and it has two classical configurations. Well, the first one is linear Halbach array, and the second one is a circular Halbach array. So the linear Halbach array is a special arrangement of the permanent magnet, and it can generate a magnetic field, very strong magnetic field in one side and almost zero in other side. And for the circular Halbach array, which can generate is a circular arrangement of the permanent magnet, which can generate a magnetic field within the center hole and almost zero outside the ring shape. So due to its special or unique configurations and properties, so it is valuable for many engineering applications. So first of all, in the medical fields, people have the magnetic resonance imaging, which is MRI, and in nuclear physics, so they have the particle accelerator, and also the NMR, nuclear magnetic resonance. And also in public transport, they have the magnetic elevation, which is like the magnetic train in the Shanghai, and also in the power and in the energy field, we have the Halbach array PI motor. And even in our daily life, it is very common to see the Halbach array. So for example, there's a refrigerator magnet, right? I believe everyone has it in your home. And so move to the research motivations. And the structure of the electromagnetic system is so complex and sophisticated, so it's highly relied or depends on the researchers or engineers' experience and intuition. And here we give a solution which topology optimization can provide a precise and automatic framework for Halbach array design by optimizing the shape and distribution of the permanent magnet shape within a given design domain. And also the permanent magnet arrangement with different magnetic direction also present a challenge for design. Here, so let's move to methodologies. So here, first of all, we would like to modeling the circuit Halbach array. So the magnetic system is employed to model the circuit Halbach array, and the magnetic system can be represented by the two of the Maxwell equations and one constitutive relations. Well, the first Maxwell equation is Faraday's law, so that is a changing magnetic field can generate a circulating electric field. And the second one is the divergence of B equal to 0, so that is Gaussian law of magnetism, so that means the magnetic monopoles does not exist, and the net magnetic flux through any closed surface is equal to 0. And that's one constitutive relations, and that's the partial differential form of the governing equations, and also that's the weak form of the governing equations. I will give more details in the next slides here. So here is our design objective, so which is topology optimization problem formulations. So the right-hand side picture is our boundary conditions, and the red region represents PM region, and the blue region represents the air region. And you can see the shaded area is our design domain. And our objective function is maximize the vertical direction magnetic flux within the center hole. And it is subject to the this governing equation of the magnetic system. So what does this mean of the governing equation shown here? So we can see the left-hand side is energy by linear form, and the right-hand side is source linear form. So the meaning of this governing equation is the magnetic energy is done by the source current or magnetization effect. And here I would like to introduce the shape and topology optimization of circuit Halbach array. So if you're familiar with the topology optimization, so you might know there's a lot of method for topology optimization. So people have the density-based method, or maybe homogenization method. And in our lab, we focus more on the level-set-based method. So the level-set-based method is using a higher dimensional function to represent a 2D design domain. So we can define as when the phi, well, this is the level-set function. So when the level-set function is larger than 0, we can define it as the material region, and it is smaller than 0, we can define it as a void region. And if the phi is equal to 0, so that means the boundary between the material and void. And the evolution of the boundary dynamics governed by the Hamilton-Jacobian equation, which is shown here. And the Vn is our normal velocity field, which can be determined by the sensitivity analysis. And here we're using a Cardinal basis function parametric Lefson method. So we know there are some drawbacks of the conventional Lefson method, which is the step size need to be very small, and it also need a reinitialization scheme to maintain the numerical stability. And here we're using the Cardinal basis function to, instead of solving the PDEs, we're solving the ODEs, which is like save more computational cost. And no need of the reinitialization scheme, and it also have the physical meaning of the design variables. Okay, so let's move to the shape and topology optimization of circular Halbach array. So I would like to review our object function, which is maximize the vertical directional magnetic flux in the center hole, which is in omega 3, shown on the right. And so when we're doing the topology optimization, we usually identify different material with different material properties. For example, if we're doing the solid mechanism problem, so different material, they may have different density and Young's modulus. And in this particular example, we know there's a one constitutive relation of the permanent magnet, which is, we have the BR, which is the key factor of this PM, which is called remnant flux density. So that is a vector, and it's come with one magnitude and one multiplied by the directions. So we can define it as when the Lefson function is larger than 0, so you can represent this PM1 with magnetization direction 1, and less than 0, it can be represented PM2 with magnetization direction 2, and equal to 0, that is boundary between the two permanent magnets. And here, well, we need using Lagrange multiplier method to reformulate this PD constraint problem to an unconstrained problem. And here we also need to do the material derivative to derive the sensitive analysis. So yeah, and I'm not going to go through all the mathematical details. Yeah, and that's the final normal velocity field we calculated by using the steepest descent method. And we also need the Eigen-based method to solve this Eigen variable. We can give a better computation of the topology optimization. Okay, let's move to numerical result. Well, the first one is optimization with shape only, so which means the magnetization direction is fixed. We only optimize the shape of the permanent magnet. Well, here we're using conformal mapping, which is mapping from the irregular design domain to a standard design domain, from the quarter ring shape to a rectangular shape. And that's the first example. We can see there's two colors. This orange color and blue color represent the two permanent magnets, and this white arrow and the black arrow represent the two magnetization directions. And this is mapping back to the original design domain. And these four colors represent the four permanent magnets. And total take 100 iterations. Yeah. And this is in the standard design domain, and this is in the original design domain. And we can see that's a CAD model of the optimized design, and that is finite element simulations. So let's do a performance evaluations. Well, that's the convergence plot. Well, this one is reference design, and this one is optimized with the shape only. So for the reference design, the performance calculated is 1.499 Tesla, and for this optimization with the shape only, the final performance comes to 1.51, 18 Tesla. So it's like a 6.47% improvement. So not bad, right? And we feel like it is not enough. So is there a chance we can add the magnetization direction into our additional design variables? So because we believe more design variables can give us more freedom or space to improve our performance. And here, I will show the second example. So we show optimization with both shape and the magnetization directions. So we can optimize the shape and magnetization direction simultaneously. Here we're using our idea is quite straightforward, which is using analytical sensitivity Eigen method for shape optimization, and using finite difference method for magnetization direction optimization. So the reason why we're using the finite difference method for magnetization direction optimization is because finite difference method is more straightforward and which is easy to handle the fewer design variables. And here, considering the robustness of the finite difference optimization, we introduce a decaying learning rate, which is alpha k, shown here. And it can stabilize the early iterations and also reduce the chance of the oscillations with optimization goals, and also improve the convergence reliability. Let's see the result we got here. And you can see that's the optimization we can see there's two colors represent two permanent magnets, and these two arrows, you can see the swing of the arrows. So that means they optimize simultaneously with the shape. And this is in the original design domain. And that's also the current plot. And and that's a CAD model of this optimized design. And also we have the final element simulations. Let's see the performance of the three designs. So we can see this one is reference design, and this one, second one, is optimization with shape only, and third one is our newly optimization with both shape and magnetic directions. So the performance for the first one is 1.41 Tesla, and for this one, optimization with both shape and magnetic directions, it comes to 1.55 Tesla. So it's about 9.38% improvement. And also you can see the color scale. So the color is coming within center hole, becoming darker and darker, and the magnetic flux lines becoming dense and become straight and dense, right? You can see here it's more like a curved line here, a curve here, and becoming dark and dense. So we feel like it is still not enough. So because we know when we are in collaboration with the GE Vernova, there are some people said, so we believe that more magnets can give additional controls of this magnetic flux. So I'm thinking, why don't we do a multi-material topology optimization of the circuit Halbach array? So here we're using the color level set based method. So we can see the red color and green color. There are two level set functions, and this one shown in the D is their combination of the two level set functions. So the two level set function can represent the maximum is 4 materials. So we can see it can be 1, 2, 3, and 4 materials. And let's see the final result we got here. Well, that's in the standard design domain, and this is in the original design domain. And that's from iteration 1 to iteration 100, and these three colors represent the three different permanent magnets, and also mapping back to the original design domain. And and that's the final CAD model. So these 6 colors represent the 6 permanent magnets, and this is the final FE simulation of this optimized design. It total take 100 iterations, and let's do performance of these four designs. So from the reference design and for this multi-material design, we can see the performance come to the 1.66 Tesla, which is 17% improvement compared with the reference design. And here I made a histogram, so we can see the improvement of this design from the reference design to the final multi-material topology optimization design. And and we can see the color of the color scale is becoming darker and darker, and also the magnetic flux lines becoming more and more dense and straight within a center hole. And that's the 3D prototype here. So also from reference design, optimization with shape only, and optimization with both shape and magnetic directions. And the final one will be multi-material topology optimization. And here I would like to make a conclusion here. Our contribution, we're integrating the level set based method of topology optimization with the circuit Halbach array design, and also we take the magnetic direction into consideration as our additional design variables. And the third one is the multi-material topology optimization provide great control over this magnetic flux distribution. And thanks. And this is me, and this is my supervisor, Professor Shi Huichen, and this work is sponsored by the U.S. Department of Energy and the National Science Foundation and the GE Vernova. I would like to stop here and refer to any questions.
Any question for the speaker?
I have a question.
Yes.
So during the optimization, you showed how at the beginning there are some localized circular regions.
Circular region, yeah.
Disappear. So do you initialize it like that, or is there any reason for that?
Sorry, I didn't get
So
the
do you
question.
initialize it like that? So you can go to the slide of the optimization. Yes, this one. For
Yeah,
example,
this one.
in iteration 1 there are these localized regions,
Yes.
and iteration 100
Yeah.
it has changed. So do you do any specific initialization?
Actually, we're using the conformal mapping as I mentioned. So we're mapping from this original design domain to the standard design domain, which is only for our convenience we're easy to define the levels of function. I'm not sure I answered your question or not. But our final element simulation is still doing in the the original data domain, only the optimization doing the standard data domain, and we are conform mapping, which is a step by step, in each iterations.
Yeah, I'm referring on to the picture on the top right. So in
Yes.
iteration 1, you see that the distribution is different than iteration 1 had.
Well, okay, yeah. You may curious why in the iteration 1 they have the like some circular feature, right?
Yeah.
I mean, like, well, that's the key, well, I think that's the characteristic of the level set-based method, which is we need to drill some holes at the very beginning, which can easy to handle the topological change. So topology optimization, which is like, for example, in this picture, they have a lot of topology, right? And after optimization, so the topology is becoming like from for example from the 20 to 3. So that's called topology optimization. Yeah.
Okay, thank you.
Yeah, and that's just initial design. So yeah.
Okay. Any questions? Final confirm. We don't have the presenter from the Naval Research Laboratory, do we? We don't. Okay. Any question for the speaker? If not, let's thank the speaker again. This concludes our section, and then if you are interested in this topic, we are going to have a committee meeting at 6:10 in Montreal room. So welcome to join us. Thank you.